Today we talk about an extension of the spectroscopy that we learned in the last class. In the last class we talked about the basics of the spectroscopy. So today we'll dive little bit deep inside what are the different kinds of spectroscopy. To start with, if you remember, we talked about a single atom, and a single atom you can actually tell about a single atom by its Bohr model. So you have the neutron in the center of that atom, and then you have the electrons which are surrounding this nucleus. Okay, so you have a structure like this, and this is the model which is known as the Bohr model. Okay, so Bohr model is the most basic way of understanding how does the light tissue interaction occurs. So in this, for example, you are shining, one is actually shining this packet of energy that is also known as the photon. So if you shine this packet of energy to this atom, one of its electron will actually go from the lower, which is the more stable shell, to the higher shell. Okay, and after some time it again goes back to its original shell, that is innermost shell, and then when it is coming back to its innermost shell, it actually again emits that a particular photon. So this is a case when we talk about in the case of Bohr model, right. So there are different ways of representing the same phenomena. Another model which is also known as energy band diagram model, it is when we talk about, especially when we talk about molecules now. So in this we have x-axis which is internuclear space, and y-axis as the energy. Okay, so over here you can see that it's represented in this format. So you have the wells like this. Okay, they are not that much spaced apart, but something like this. Okay, so these are the wells, and these structures are known as the electronic states. So S0 is a ground electronic state, and S1 is the first excited electronic state, and each of these electronic states are divided into small parts. So here you can see they are divided into small levels actually, like this. Okay, these levels are known as vibrational levels. So this vibrational level V0, V1, V2, V3, V4, and so on and so forth. Similar to this, you have V0, V1, V2, V3, V4, and so on and so forth. The one that you see S0 and S1 is known as electronic states. Okay, this is the ground electronic state, and the one that you see over here is the first excited electronic state. Okay, so and the one that you see in the green color, these are the vibrational levels. Okay, so each electronic state have its own specific vibrational levels where the electron can actually survive, and you can see if you would like to see the probability of electronics to survive on those particular vibration levels, you will see that it would be something like this, for example, and then it will be something like this. So it actually comes up based on the probability. Okay, similar to this, you will see that you have similar over here. So you have 2 peaks, then you have 3 peaks, and then so on and so forth. Okay, so the peaks that you see over here, the peak actually represents the probability for the electron to survive at that particular internuclear space. Okay, so it's for the ground vibrational level, it is highly probable that the electron will be surviving somewhere in the center over here. Okay, while on the top it would be like there are two positions that it has equally probability to survive, right. So this diagram that you see on the right hand side is known as energy band diagram. Okay. So either you can use Bohr model or you can use energy band diagram to represent how the light actually interacts with the tissue. Let us use this energy band, the information that we learned right now on energy band diagram, and from there let us understand to see how we can talk about different kinds of spectroscopy. The most simplest kind of spectroscopy, as you can see, you can say in terms of energy. So again, let us draw this energy band diagram. Okay, so this is internuclear space. This is the energy, and what I do is again I draw these wells. And then I draw these levels. Okay. Now let us assume that the electron is somewhere sitting over here, and you give a photon of a particular energy. Okay, so we are giving a photon, that is a packet of energy, and that has a particular energy. So that particular photon has a particular energy, and you know actually that energy is nothing but h c by lambda, right. So h is the Planck's constant, c is the speed of the light, and lambda is the wavelength of the photon that you are shining on the particular electron, or that you are shining to this molecule. For example, this is that molecule, okay, and you are shining this particular photon to this particular molecule. Okay. So what will happen within this molecule? Just you can pause this video and just try to see, or just try to think about what is the interaction that could happen over here. Okay. So the things that you can start thinking of is how much is the energy that we actually give in the photon. And as you can see here, energy is inversely proportional to the wavelength. So lower the energy, higher the wavelength. Okay. So now let us digress a little bit and try to understand. For example, you have a blue light or a photon which is of blue color. Okay. So over there the wavelength is around 450 nanometers. Okay. The energy associated with 450 nanometers is around 2.8 eV, right. Now let us talk about red light, red photon. Okay. Okay, instead of light, let us tell it as a photon, that is better. Okay, so now the red photon is around 650 nanometers, for example, and if you convert this into EV, your energy is around 1.8 EV. Okay. Now let us talk about NIR, that is around we talk about. So this blue NIR is again NIR photon. Okay, that would be around 850 nanometers, 940 nanometers. The energy is even lesser, that could be around 1.2 eV, for example. Okay. So as your wavelength, as you see, if as the wavelength is kind of increasing, you can see the energy is kind of decreasing. Okay. Now let us shine the photon, this photon that I am talking about, the photon that we are shining right now to this molecule is of the lowest energy, right. So lowest energy like around 1.2 eV, that is we are shining the wavelength of infrared on this particular molecule. So what will happen is that the energy is so less that this electron at the lower most vibrational energy level of this ground electronic state. So this is S0, this is S1, right. So it doesn't have so much energy, so it cannot come out from this, it cannot do that, it cannot come out of this well. So what it will do is that it will just come to another vibrational level energy, and it will just stay there. and as it has gained some more energy, it will actually now lose the energy in form of vibration, right. So it will actually so there are so what will happen, let me just draw it first. Okay, so it will move to the up part, any of the upper vibrational levels, for example go from V0 to V2 for example. So this is V0, V1, V2, and as it has gained some more energy, now it that particular molecule will start to vibrate. Okay, this will start to vibrate because it has a particular energy now, right. Now it has to lose that particular energy because of law of conservation energy. So it has to lose that particular energy that it has gained because of the interaction of this photon. So it will start to vibrate, right, and because of this vibration its temperature kind of little bit rises, right. So so this kind of interaction that you see is known as infrared spectroscopy. Okay, why it is kind of known as infrared spectroscopy? It's because you are shining a light which is in order of like infrared wavelength, and you are staying within the vibrational energy levels, right. So it's also known as vibrational spectroscopy, or it's called as also infrared spectroscopy. Right. So here what is the main important thing that we see is that the electron do not come out of the ground electronic state, it just survives in the bottommost ground vibrational energy level, right. Now let us again draw one more example of this internuclear space, and then we have the energy, right. Again we draw this bands. Okay, and let us draw these energy levels now. Okay, this is S naught as we discussed earlier, this is S1, right. Now let us see what will happen to this electron. Again this electron is there. If you give little bit more energy, here you can see that we give only around 1.2 eV of energy. Okay, this energy that we gave over here, this energy that we gave over here was around 1.2 eV. What if we give more energy? For example, in the visible range, it goes into the visible range. For example, we give around green light, for example. Okay, we give around green light. For example, we have this photon now. Okay, it's represented by a particular energy, and that green light could be around 2.3 eV, for example. Okay, this is around 2.3 eV we are giving to this. Yeah, so we now give a photon of green color, that is energy which is around 2.3 eV, and let us see what will happen. So which is now comparatively more as compared to 1.2 eV. So what will happen is that this photon will have significant energy to come out of the electronic state, ground electronic state, and it can actually jump to a higher electronic state, right. Now it can either go to the another electronic state, or it can actually, it would be just sufficient to lie somewhere in between of this, between the two electronic states, right. It can happen both the ways. So if it has significant energy, it will go and move to the first electronic state. If it doesn't have significant energy, it will lie somewhere in the center. Okay. Now, so for example, let us see what will happen if it actually goes, if we have, it doesn't have that much energy, and it will actually go somewhere over here in the middle of both the electronic states, right. So now, so example, this one is over here. So this state that it actually survives for some time and then actually comes back to its original ground state, this state is actually known as virtual state. Okay, why it is known as virtual state? Because it's not observable. So it will be going to this particular state of energy, and then it will jump back to its original wavelength after some time, right. So let us try to see the variance of this kind of jumps. Okay, again, so for again what we will do is we will draw this band diagram again. Okay, and let us do a more broader over here. So it's that, so we can actually show multiple variations of this particular jump. So what I am saying, okay, let me just draw tell about this. So this internuclear space, and this is energy, and this is again the photon which is jumping from here to the virtual state. So this is virtual state. Sorry. Okay. So what will happen over here is that I'm going to give a green light for it to this my my molecule, and it will absorb the energy, and the electron will move from the ground vibrational level to a virtual state, that is between my two electronic state. Okay. After some time it will jump back to my original vibrational level. Okay. Now what I'm going to do is that I'm going to shine a photon of wavelength of green, so it would be around 2.3 eV, right. Now as it is going to make the upper jump of the same height as the compared to the while it is going downwards height or the energy. So the energy that it will be giving out would be almost the same, or it would be exactly the same actually, because we are now talking about in terms of quantum mechanics. So it would be exactly the same, and it would be the same green color that you will get. So you shine the green light and you actually get the green light out of it. Okay. So this phenomena is known as Rayleigh scattering. So it's kind of a scattering. Okay. This phenomena is known as Rayleigh scattering, that the electrons are going from the ground state to higher state, and then again this higher state is nothing but a virtual state. So it goes from ground state to virtual state, and then again jump back from the virtual state to the ground state. Now there could be another variants of what it could happen. For example, the electron in the just one above the ground vibrational level, it can also jump, okay, and it will come back to the ground state. Okay. So this you can see that the jump over here on the on this particular, okay, let me just use the laser, or this particular jump is kind of lower energy as compared to the right hand side, which is of higher energy comparatively, right. So what you will see is that it will have a little bit minor shift in the energy of while it is emitting. Okay. And there could be another variant again. For example, it could actually jump from the ground state to the another same virtual state, and then it will actually jump back to just one step before the ground state, and then it will again jump back over here, right. So here you can see that again the photon that will be emitted would be of lower energy, right. So what you see is that this energy that you see over here, it would be 2.3 eV plus delta E. Some more energy would be there, and in this case it would be 2.3 eV minus delta E. So little bit lesser energy would be there as compared to the actual green color. So now you have the green color that you are shining, and what you see is that while it is interacting with this molecule, there is a change in energy. Now this change in energy is nothing but change in the wavelength, right. So if you see over here, this particular kind of scattering is known as Raman scattering. Okay. So whether it is this case on the so if you say that it is case A, this is case B, and this case C. Okay. So this case A A is nothing but Rayleigh scattering, and case B and C are the Raman scattering. And Raman scattering, as you see, there are two variants of Raman scattering. One is known as Stokes scattering, other is anti-Stokes scattering. The one with higher energy is Stokes scattering. The one with lower energy is actually anti-Stokes scattering. Okay. Now let us try to understand if it has sufficient energy that it can now jump from the ground energy, ground vibrational energy level to an electronic state of another of excited electronic state, right. So let us again draw this vibrational again let us draw this energy band diagram. Okay, so something like this. Okay, so here again you have energy, internuclear spacing, and then you have this, sorry, okay. So now what will going to happen is that you are again going to shine a photon, okay, and you're going to shine a photon to this molecule, and the electron from the ground vibrational energy level from your electronic state 1 will actually move to the higher energy level. Okay, okay. So actually it has to be somewhat similar to this. Yeah. Okay. Now it will go to the vibrational levels of higher electronic state, that is excited electronic state, and then what will happen is that it will kind of do the it will make some kind of smaller jumps. This is known as thermal relaxation, and then it will again jump from a particular energy level, that is the ground energy level, to the ground electronic state, right, and this will again emit the photon. Okay. So now for example you are shining an energy of for example you are shining a photon of blue color, it is around 2.8 eV. Okay, and so this is a blue color photon that you are shining. It's significant jump you see to this electron, and then it will do minor jump, that is thermal relaxation it will undergo, and this is the interstate. So it's kind of it will survive for some time over here, and then it will make a jump over here. So here you can see this jump is kind of less as compared to the jump that it actually makes to reach above, right. So you shine energy that is blue color, but what you actually get over here is going to be of lower energy. Lower energy means higher wavelength, right. So the wavelength that you see over here, for example, it could be for example, if shining blue, it could be green in color, for example. So it would be around 2.2 eV, for example. Okay, 2.2 eV, right, which actually may represents the green color. Okay, so this kind of phenomena is known as fluorescence. Right. Now, similar to this energy band diagram that we are drawing, this alternate approach to draw the same thing, and that is known as Jablonski diagram. And this is what you would actually see in most of the places, that is known as Jablonski diagram. And instead of this energy band diagram, it's very much similar to the energy band diagram, just the representation actually changes. That is, now you have again you have vibration energy levels, you have V0, V1, V2, V3 of your ground electronic states, and then again you have, after some time, you have vibration, another set of vibrational levels of energy of the excited electronic state, and then you give a photon of energy, for example, for this one to this one, for example. Oh, sorry. So you move from here to here. For example, this one you see over here. So this, and it then just absorbs this much of energy. This is known as infrared absorption, infrared or vibrational spectroscopy or infrared spectroscopy. Now, if the electron is moving from here to one virtual state, and then it moves from that top to the bottom to the same energy levels, this is known as Rayleigh scattering. Okay. Now, if it is going from a smaller state or higher state of vibrational energy levels and then moves back to a bigger jump, for example, like this, then it is known as and another variant is this one. So it actually shines, you move from here, okay, and you jump with lower energy, right. So both of them are known as Raman spectroscopy. Okay. So either it is making a bigger jump, then it is a Stokes shifted, or if a smaller jump, then it is anti-Stokes shifted. Or it could actually go to the electron actually can go to the higher electronic state, and then it can make little bit minor jumps, and then it will kind of jump back to the ground vibrational energy level of the ground electronic state, right. So this is just the photon that we are shining, and each of this process will actually emit a photon. And the final one that I was talking about is fluorescence. Fluorescence spectroscopy. So all these variations are a part of spectroscopy, infrared spectroscopy, that IR spectroscopy, visible spectroscopy, as well as fluorescence, as well as Raman spectroscopy, right. Okay. So this is what I would like to talk about the spectroscopy part. Thank you.